Gnanam paramam dheyam. Knowledge is supreme.
So, let us look at dissolution of, let us see how to capture this behavior. Dissolution of polydispersed particles. So, what is polydispersed particles? Suppose you have collection of particles which are of different sizes. For example, this big one could be of size d1, it could be d2, maybe it could be d3, and this could be d4, and so on and so forth. So, there will be a collection of particles, and each of these are different in size, and so there are particles of different sizes. Now, not just at the initial stage, that the particles will be of different size. There will be a distribution of sizes of particles all through the time when the dissolution is actually occurring. So, therefore, clearly there is a distribution, there is a size distribution, and the question is to find out what is the dissolution time. The objective is to find the dissolution time, and in order to find the dissolution time for particles who are actually placed in a certain distribution, one needs to actually follow the distribution dynamics. So, the distribution dynamics have to be followed. So, let us look at what is a distribution. So, suppose if I look at the plane of number of particles versus the fraction of the number of particles that are actually of a particular size. So, then we expect that it is a certain histogram, where the location between, let us say, dp and dp plus delta dp, which is a small increase in the particle, small difference in the particle size. So, in that case, the area under the curve in this location, it signifies the number of particles which are actually present in the system whose diameter is between these two numbers. So, therefore, f dp multiplied by delta dp, that is basically the number of particles between dp and dp plus delta dp. So, that is the number of particles, and moreover, if we integrate this expression from 0 to infinity, f dp into dp into the differential of diameter of the particle, that should be equal to n naught, which is the total that is the total initial particles which are actually present. Now, if we assume that it follows a log normal distribution, let us assume that the initial distribution of the particles, they follow a log normal distribution. Let us assume that they follow log normal distribution. So, now the fraction of the species, fraction of the particles whose size is dp at time t equal to 0, and that normalized by n naught is actually given by 1 by dp square root of 2 pi into ln of sigma 2 multiplied by exponential of minus ln of dp by dg and square of that divided by 2 times ln sigma 2 square. So, that is the expression for the log normal distribution, where dg and sigma 2 are essentially the distribution parameters. These are the distribution parameters. So, now the question is, in order to find out what is the dissolution time of the particles which are actually in this polydispersed system, is to actually find out what is the how the distribution itself changes. Instead of monitoring every drug particle, it is better to monitor simply the population itself. So, the question is, how does the distribution change? So, that is what we are going to look at. Now, suppose if we look at the distribution, at any time, and if it is some general curve like this. Now, we can write a simple balance on the population of these drug particles, and suppose if we take a small element between dp and dp plus delta dp. So, therefore, the thickness of this element is delta dp, if we assume that the thickness is delta dp, and by definition of this histogram, the integral of 0 to infinity f of dp comma t into the d dp should be equal to n naught. That should be the total number of particles that were actually initially present, and because there are no new particles are added, it is only the particles actually dissolve and disappear. So, therefore, the integral under the curve up to infinity, if we assume that the particles are actually of some finite size at all times, then that should be equal to the total number of particles itself. Now, if that is not the case, then this should be a function of time. So, the number of particles will change because some of these particles will dissolve and disappear, and when that happens, then this integral between 0 to infinity should actually be a function of time. Now, one other quantity which is required in order to model this system is the growth rate. Suppose r dp is the growth rate of every particle, and of course, it depends upon the size of the particle itself. So, that is the growth rate. Growth rate of particle whose diameter is dp, then one can actually write a population balance equations. In order to capture the dynamics of the whole distribution itself as the reaction actually proceeds. So, the population balance equation can be written as the balance between the number of particles which are actually growing and reaching the diameter whose size is between dp and delta dp. And also we need to account for the particles which are already present in this small element dp and delta dp, and they grow and they actually become bigger than dp plus delta dp. So, which means they leave this small element delta dp, and there is no addition of new particles, because once the drug is being fed, it is just being dissolved, and so there is no other mechanism by which the particles are actually being added into that small element delta dp. And then the other term is the accumulation term. So, therefore, putting them all together, it will be number of particles growing into region between dp and dp plus delta dp minus the number of particles growing out of region between dp and dp plus delta dp. That should be equal to the accumulation of particles in delta dp in that small element. Now, suppose if r is the growth rate, which is what we have defined a short while ago, then the number of particles growing into the region between dp and dp plus delta dp is actually given by r into dp. So, that is the growth rate when the particle is whose size is exactly dp, and then that multiplied by the corresponding fraction will provide a clue as to what is the number of particles that are actually growing into the region in this small interval of diameter, and that evaluated at dp minus delta dp, and that should be equal to d by dt. So, that is the accumulation of the particles in delta dp equal to f of dp comma t multiplied by delta dp. So, that is the rate of change, that is the rate at which the particles are actually being accumulated in that small element. So, now rearranging this equation and setting delta dp equal to 0. So, set delta dp to be 0, then it can be written as minus d by d of the particle diameter into f of dp comma t, that should be equal to dou f by dou comma t. So, that is the expression for the that is the population balance. So, now what do we do with this population balance? So, we can solve this equation in order to find the radius of the particle, in order to find the how the distribution the radius distribution actually changes. So, now this can actually be rewritten as df by dt plus r into df by d dp plus f into dr by d dp, that is equal to 0. So, now where r dp is essentially the growth rate of the particle of size dp, and if suppose in the earlier case if the particles were monodispersed, we actually found out what is the growth rate. So, therefore, for every particle of a certain size, that expression can be used to used as a growth rate of the particle of that particular size. So, therefore, from here it will be d dp by dt, that should be equal to minus alpha by 1 plus dp by d star. So, that is the rate at which the monodispersed particles are actually growing. So, plugging that into the expression, plugging that into the population balance, we will find that, so this is for the monodispersed case. So, plugging that into the expression, we will find that the rate of r dp, that is equal to minus alpha by 1 plus dp by d star, and so the population balance will be df by dt plus minus alpha by 1 plus dp by d star into df by d dp plus f into alpha by d star into 1 by 1 plus dp by d star the whole square, that is equal to 0. So, that is the expression for that is the population balance that actually captures how the dynamics of this distribution actually changes with time, how the distribution changes with time. So, now if we introduce a few dimensionless quantities, which is actually useful in solving this problem. So, psi equal to f into d star divided by n naught, where f is the distribution of the particles based on the size, and d star is the ratio of the diameter when the mass transport rate and the reaction rate are equal to each other, and n naught is the initial total number of particles. Then epsilon is defined as 1 plus dp by d star, and theta is defined as alpha into t by d star. So, now if we introduce these dimensionless quantities, we can rewrite the population balance as d psi by d theta, that is minus 1 by epsilon into d psi by d epsilon minus that is equal to minus psi by epsilon square. So, that is the expression. So, this equation is actually of a very familiar differential equation form, which is of the form P of x comma y into dz by dx plus q of x comma y into dz by dy, that is equal to r of x comma y comma z. So, from here we can see that if p of x comma y is nothing but 1 and q of x comma y is like 1 by epsilon and the r of x comma y is like psi by minus epsilon square. So, the way to solve this equation is basically to use the method of characteristics. Where it is this problem is posed in a slightly different way. So, dx by p d theta by 1 is equal to d epsilon by minus 1 by epsilon, and that should be equal to d psi by minus psi by epsilon square. So, that is the way in which the population balance equation, which is actually written here, can actually be posed in terms of the method of characteristics. So, now the first two terms in the repose problem, basically it looks like d theta by 1 is equal to minus epsilon into d epsilon. So, from here we can find out that epsilon square plus 2 theta is equal to a constant C 1, and that should be of the form h of epsilon square plus 2 theta. So, that should be the functional dependence of this particular expression. And then next let us look at the other case, d epsilon by 1 by epsilon, that should be equal to d psi by psi by epsilon square. So, this can actually be rewritten as d epsilon by epsilon is equal to d psi by psi, which can be solved to obtain ln epsilon equal to ln psi, and that is equal to some constant k. So, that is a constant. So, from here we can find that psi by epsilon is nothing but some constant C 2, and that can be equal to h of epsilon square plus 2 theta. So, that is the functional dependence. So, next we can actually see how to take this forward and find the distribution profiles. So, suppose if we can rewrite the relationship between the psi and epsilon as psi equal to square root of epsilon square into h of epsilon square plus 2 theta. So, in order to obtain the final distribution, which is actually present in the definition of psi. So, psi is almost like a non-dimensional distribution of the various size of the particles which are of different sizes. So, if you look at the initial distribution, which is actually given by log normal distribution. So, the log normal distribution is as it goes here. Root 2 pi into ln sigma 2 into exponential of minus ln dp by d star dp by dg the whole square divided by 2 ln sigma 2 and square of that. So, that is the initial distribution. Now, if you know the initial distributions, then we can actually introduce the transformed variables. So, basically we introduce epsilon, psi and theta into this initial distribution, and if we assume that if we assume that epsilon equal to 1 plus dp by d star. So, this comes from the non-dimensional form of epsilon. Then from here we can get that dp is equal to d star into epsilon minus 1. Actually, this is the non-dimensional form of epsilon, and from here we can find out the relationship between dp and the other parameters. So, if we assume that dr, if we assume a new variable dr, is equal to dg divided by d star, where dg is some parameter of the distribution and d star is the diameter at which the mass transfer rate and the reaction rates are equal. Then we can find out that psi is equal to some f of epsilon comma theta divided by n naught into d star, that should be equal to square root of epsilon square into h of epsilon square plus 2 theta. So, that is the functional form of the this variable psi. So, now if we want to find out what is the final distribution, we need to find this expression f of epsilon comma theta. This expression needs to be found in order to find out what is the instantaneous distribution of the sizes. So, how can we do this? So, it can be done by actually using the distribution at the initial state where the reaction has not started, then f of epsilon comma theta. So, this can be obtained by simply replacing epsilon square with plus 2 theta in f of epsilon comma 0. So, note that this is the initial distribution and the final distribution can simply be obtained by replacing epsilon square in this initial distribution with epsilon square plus 2 theta. So, that serves as the solution methodology. So, now we can rewrite this as psi of epsilon comma theta. So, that is equal to f of epsilon comma theta. So, you can introduce, we can now use the initial distribution in order to find out what is the value of psi, what is the expression for psi as a function of epsilon and theta, and that would be equal to epsilon divided by square root of 2 pi into ln sigma 2 into 1 by square root of epsilon square plus 2 theta into 1 by square root of epsilon square plus 2 theta minus 1 multiplied by exponential of minus ln of square root of epsilon square plus 2 theta minus 1 by dr and square of that divided by 2 into ln sigma 2 to the power of square of that. So, that is the distribution at any time in the non-dimensional form. So, once we know this distribution, we can look at the distribution profiles as a function of time. So, suppose if this is dp, the particle diameter, and this is f of dp comma time, then if suppose this is the initial distribution, so that is time t equal to 0, that is the initial distribution. Then as time progresses, all the particles are actually undergoing the dissolution because of the heterogeneous reaction, and so as time goes by, the distribution changes, and so this is T1 which is greater than 0, and then as time further goes by, more dissolution will happen, and so this will be T2 which will be greater than T1. And then further time elapses, and then the distribution will be, this will be T3 which is greater than T2, and then eventually when the conversion is going to be almost complete, then the distribution will look like this, where this is T4 which is greater than T3. So, that is the kind of distribution that one can actually obtain as a function of time for this polydispersed particles which are undergoing dissolution. So, let us summarize what we have learnt in the last 3 lectures. So, we have looked at the fluid solid non-catalytic heterogeneous reactions, and this can occur through 2 modes. One is where the particle size does not change, another one is the case where the particle size actually changes as the reaction progresses. And there are 3 different possible resistances which are actually existing in this kind of a system. One is the gas film resistance for diffusion resistance, and the other one is the ash layer diffusion resistance, and the third one is the reaction controlling resistance offered because of the surface reaction. So, these 3 under these 3 regimes, the time that is taken for the time that is taken by the particle to reach a certain radius has been modeled and calculated, and that for different geometries have been looked into for both the shrinking or the changing size particle case and for the constant size particle case. And then we looked at an example of dissolution of monodispersed particles and extended for a polydispersed system. Thank you.